Module 5, Model Development Methodology. Welcome back to the channel. Those who haven't yet subscribed, please do so and click the like button, and don't forget to share the content with your colleagues. Okay, let's dive into it. When people talk about BIM, they talk about 3D models, but BIM is not about how detailed a component looks. It's about how efficiently information is structured, managed, and reused throughout a project. In this module, we're going to look at model development methodology, how Revit models should grow over time, how much detail is appropriate at each stage, and why less geometry almost always creates better BIM. The purpose here is to explain why certain modeling approaches are better than others and how those decisions affect performance, coordination, and long-term usability of the model. We'll look at how geometric complexity impacts file size and speed, how metadata and 2D line work enhance model value, and why BIM should prioritize structured information over AutoCAD-style drafting habits. The key concept introduced is grading of components, building models in stages, using simple placeholders first, and only increasing detail when it is genuinely required. The key objective of this module is to promote a simple but powerful idea. Users should prefer less 3D geometry, not more. BIM efficiency is defined by the performance of the components inside the model, not by how impressive they look in isolation. By the end of this module, you should understand how to structure a Revit model that remains fast, stable, scalable, and suitable for multiple downstream uses. Keynotes: is BIM just about 3D? A common misconception is that BIM is primarily a 3D modeling exercise. In reality, BIM operates across multiple dimensions of information, often referred to as the Ds of BIM. For practical purposes, there are 6 that have broad industry agreement. 1D represents points, 2D represents line drawings, 3D introduces model geometry, 4D relates to time and sequencing, 5D covers cost, and 6D relates to facilities management. Not every project, discipline, or stage requires all of these dimensions. Effective BIM is about applying the right amount of information at the right time. Model use across project lifecycle. One of the strengths of BIM is that the same model data can serve multiple stakeholders: architects, engineers, quantity surveyors, contractors, and eventually facilities managers. However, each of these uses places different demands on how the model is constructed. A concept architect's model is fundamentally different from an FM handover model, and trying to satisfy all possible future uses from day one is neither practical nor cost-effective. Revit supports a far better approach, allowing components to be swapped and enriched with metadata as project requirements evolve. Information timeline and overload. The McLeamy curve illustrates how BIM enables earlier decision-making when changes are cheaper and easier to implement. However, this does not mean that all design decisions must be made at the concept stage. Over-defining components too early, especially during tender or speculative stages, often leads to wasted effort and reduced project profitability. Revit is just as capable of supporting vague, conceptual design as AutoCAD or hand sketching. The problem lies not in the tool, but in how it's used. Over-modeling, a common BIM failure. Over-modeling is one of the most common failures in BIM adoption. Just because software allows detailed geometry does not mean that detail is appropriate. Manufacturer-supplied families are often the worst offenders, filled with seals, bolts, threads, and fine details that add no value at common drawing scales and dramatically reduce performance. BIM should remove this problem, not amplify it. For example, instead of modeling every hinge on a door, a simple generic component can carry metadata that specifies the correct hardware set. The information exists without the geometry. Conceptual modeling, how a project develops from a base template. Effective BIM workflows begin with concept-grade content. A base template typically contains only Grade 1 components, created from a very limited palette of materials prefixed with terms like concept. This allows the building form, space planning, and system strategy to develop without getting distracted by materials, junctions, textures, or manufacturer choices. The focus is placed firmly on understanding the brief and developing a successful design, not on premature detailing. Model development in waves. As design decisions solidify, components are developed in waves. First, the form is explored. Next, the model is developed. Finally, components are refined and selected. This workflow enables rapid development, supports performance stability, and allows even large models to remain manageable without complex model splitting strategies. Component grading. The complexity of components. All components should be quality checked, graded, and named before being used in a project. A well-designed family should be flexible within a defined scope, but should never attempt to cover all possible scenarios. A door family with dozens of parametric permutations may seem powerful, but on large projects it becomes unmanageable. Often, supplementing simple geometry with high-quality 2D detail delivers far better results. Graphical component grading, LOD, and grades. You will often encounter the term LOD, level of development or level of detail. These definitions are critical because they set expectations for what a model delivers at each stage, technically, graphically, and contractually. Importantly, graphical complexity and metadata richness are independent. A simple object can carry rich information, and a highly detailed object can exist purely for visualization. Grading. Overview. Grade 0 to Grade 3. Grade 0 relates to massing and schematic studies, often using symbolic representation. Grade 1 introduces concept components, generic, lightweight, and fast to model. Grade 2 replaces placeholders with defined manufacturer-specific components that remain geometrically efficient. Grade 3 is used only when rendering or close visual inspection is required and differs only in geometric richness, not metadata. Grade 4 and 5, fabrication and facility management. Beyond typical Revit usage, Grade 4 introduces fabrication data, often managed outside Revit. Grade 5 represents the as-built model used for facility management. These levels have major implications on fees, responsibility, and scope definition, and must be clearly agreed contractually. Detail, level vs component grading, coarse, medium, and fine detail levels control visibility, not model development. Trying to embed multiple LODs into a single family is inefficient. Best practice is to maintain multiple grades of the same object, simple Grade 1 placeholders, efficient Grade 2 project components, and selective Grade 3 elements reserved only for visualization. Controlling graphical display, family element visibility. Revit families allow granular control over what is visible in plan, elevation, 3D views, and at different detail levels. Importantly, many high-quality 2D representations are created entirely with linework, not 3D geometry. This allows models to remain lightweight while drawings stay clear and detailed. Case study. In this example, the 3D geometry remains extremely simple across all views. At coarse detail, a symbolic representation communicates intent. At medium detail, wall composition and glazing thickness appear. At fine detail, additional construction information is revealed. At no point does the 3D geometry become unnecessarily complex. The intelligence sits in metadata and controlled 2D detail.